Sure, let's start. So, welcome to this session of Mathematical Physics Seminar. And today we have the pleasure to welcome Valentin Féray. Valentin Féray is from Nancy. He did his PhD with Philippe Yann, who was invited some weeks ago in Marne-la-Vallée. Then after that, Valentin worked in Bordeaux and then Zurich, and now we moved to Nancy. And recently he worked on meander system, and since some people are interested in meanders here, I thought it was a good idea to invite him for us. We will hear about his work.
Thank you very much for the invitation and the introduction. So thank you for coming to attend this seminar. So indeed, I will tell you about some work I did with Valentin, which was at Uppsala University, but is now in Vienna on meandric systems. So I'm more from the combinatorics probability side. I'm not a physicist, but I hope you will be still interested in this work and which has some aspects of theoretical physics. So I will start the talk using the board and to present you the object as our page result, and then I will move to the presentation with slides. So let me do an introduction by speaking of not exactly meandric system, but an object which was introduced a bit before, which is called meanders. And meanders can be seen from different points of view, so more a bit enumerative geometric point of view, combinatorics, and mathematical physics. So I will start with the geometric point of view, and I will come back to the other point of view later. So what we will do from enumerative geometry, what I do is that I consider two closed curves in the plane and which intersect in a generical way, so intersecting generically. So what I mean by that is that I don't want to have I want no multiple crossing points, I want no tangent point or things like that. So usually no multiple crossings. The picture will look something like this. So you have one first curve, and then you have a second.
No self-crossing either.
No self-crossing, yeah. Sorry, I did.
Simple curves.
So I forgot exactly simple curves. Oh, that one. Okay? And the question when you have this kind of picture in enumerative geometry, or you want to classify them or to enumerate the number of configurations with a given a certain notion of complexity. So here that will be the number of intersection points. Okay, so the question will be classify or enumerate, we discuss the number of configuration so here, since simple closed curves in the plane have some inside and outside, you automatically have an even number of crossings. So here I will put 2n crossings. And something which a variant of the problem, something we do often with this kind of problem, is to consider rooted configuration, because to avoid symmetry, usually, so it makes usually the problem a bit simpler. Here we will see that it's still complicated. So what I will mean here, in this case by routing, is that I will distinguish one intersection point, one of the curves, and one direction. And when you do that, you see that you can number all crossing points you follow your curve or pi. So which curve I'm following, so that's this one, which is the marked one, somehow 667. Okay, and because of that, you have an equivalent combinatorial point of view on the picture. So that was the geometrical aspect. So combinatorics, you can completely rewrite your problem by saying, imagine you take your picture here, and imagine you cut. So I will cut here, and I take my first line, the marked one, and I put it straight. Or if you don't want to cut, you can imagine that you draw it. You draw the marked curve as the first long line and a circle part at infinity. Yeah?
Because you're not on the lattice.
Sorry?
You're not on the lattice, so how
yeah, I didn't put, I want to do something up to isomorphism. Or up to continuous deformation. Continuous configuration. Deformation. So then you have a finite number of yeah.
What other example do you do?
Maybe we will see it also a bit better on this picture. Should have taken more space. So one of the curves now is a straight line, and you can imagine that it's closed like this. And then I have my intersection point, which I numbered along this first curve, okay, so they are just numbered from 1 here to 8. And then here, so it's a very rather easy example, where the other curve makes something like this. And I should go 4, 5, 6, 7, 8. And I have something like this. But in fact, I could have any. I need to have something which is non-crossing on the top, non-crossing on the bottom, because I don't want self-intersection point. But I can have any non-crossing matching here and any non-crossing matching here, as long as the curve which is made like this is connected. So another example could be, and do rather complicated things. Okay, and that's a different configuration. That's really, you have no way to transform one to another without changing. It's not 8 anymore, I guess. But we can find another one with 8.
The numbers now, where are they?
Sorry?
1, 2, 3, 4, 5, 6.
The numbers are really here on the intersection point. I will have better picture on the slide in a moment. So here it's 12 intersection points. Okay? So that's from a combinatorial point of view.
Sorry.
Yes.
So defining the inside and the outside of a curve is quite complicated in the plane. I mean, the Jordan curve theorem is not trivial. So how can I see trivially that this one is not ambient isotopic or equivalent up to continuous deformation to the trivial example on the other side? Well, how to make sure that this is not just the same as going up and down a regular way?
And so I have what in my configuration here. I said I want what is configuration. Okay, so the number of and I didn't draw it here, but I have oriented. Oh, I didn't orient the second. So you have you have your labeling of the intersection points, which is well defined, which you won't change if you do a continuous deformation.
Okay, so again.
Okay, so if you think when you turn, when you take the left, when you turn left instead of going straight at the roots, you see that you're going to here 10 or you're going to 2, and you won't change that when you do continuous deformation. And you can really recover the combinatorial extent. And okay, it's, if you define precisely the good object, it's really one.
So is a configuration defined by some permutation then?
So you can define it by a permutation. So you could, for example, people are calling that meandric permutation sometimes. So you can see that, for example, as a cycle, saying this will be associated to the cycle which tends 1 to 10, 10 to 2, and so on. But it's not clear how to characterize which permutation corresponds to a meandric permutation. And another thing that you can do is, it's a bit the same, but you can read this number 1, 10, 7, 6 by following the red curves, and consider that as a one-line representation of your permutation. So meaning your permutation is something which tends 1 to 1, 2 to 10, 3 to 7, and so on. And there is a nice conjecture on the scaling limit of this permutation when you take a uniform random meanders, but it's completely open. So it's the point of view as permutation, I won't use it in this talk, but it's really interesting. So just to conclude, this combinatorial point of view and write precisely what I wanted to emphasize. So for me, so a meander is a pair of non-crossing matchings okay, so one above the line, one below the line, such that the associated graph is connected. So when you have two matching, you can see that you forget the white line. Here it's only the red picture. You can see that as a graph. Every vertex has decay 2. So this graph is just a collection of loops. And I'm calling that a meanders only if I have only one. Okay? So that's a combinatorial perspective. And from mathematical physics, maybe we want more to keep more to this picture, and you can see you can think of that as really a rooted planar 4-valent map, which is decorated with two disjoint Hamiltonian cycles. So it's a kind of loop model if you want, where you have two loop configuration. You are in a degenerate case where you want that each loop configuration is only done with one loop, and they need to be disjoint. Okay, so here it's really this picture. If you keep in mind what were you I forgot to mention. need to have, we have the vertex condition that I propose here, that at each vertex you want a crossing like this. So one of the Hamiltonian cycles should really cross orthogonally the other Hamiltonian. You cannot have consecutive edges for the map structure which belong to the same Hamiltonian cycle. Okay? So that's the model of meanders. So
when you say disjoints, it means they don't share edges.
They don't share edges. Yeah.
Okay, that's fine. So that's the disjoint.
Sorry. So as I said, one of the first questions which that we would like to answer is, at least asymptotically, is what is the numbers of meanders of size n. And this turns out to be a very difficult question, and there is a very nice conjecture there from 2000, which is due to Di Francesco. Poligny and Bitter. And the conjecture is that this should have this typical asymptotic form, so you have some constant, some growth rate, which is to the power n, and some n to minus the critical exponent. And the conjecture is what should the critical exponent precisely be. The conjecture is that this critical exponent is given by this amazing formula. So it doesn't matter what it is exactly, it's just a quadratic expression. So for me as a combinatorialist, it's really amazing to have such a conjecture. I don't know, as mathematical physicists, you may be a bit more used to that. So this comes from quantum field theory interpretation of meander, which is really using this point of view that meanders are some kind of loop configuration on a random lattice. I'm not able to explain you in details how you get these exponents. It's related interpreting meanders as elements of some quantum gravity, and you can compute the charge of the model, and then you have some formula to come back to the critical exponent. And this is, I think, completely open, and unfortunately that's not what I will. That's not the proof of this conjecture that I want to present today. Any questions so far? Okay. So when you have some hard problem for that, and you will see that there is also another motivation, you want a bit to change your approach, relax a bit the problem, and I think that's one of the motivations to introduce the notion of meandric systems. So that's not something that we introduced. I will give some reference, but which has appeared in the literature the last few years. And basically here we will start from the combinatorial definition, so it's a pair of non-crossing matchings, and we stop there. We remove the difficulty, we remove the connectivity condition. So it's a really somehow trivial object. So just write it, the meandric system is meandric systems with one matching above the line, one below the line, and to study their components. We will have something like this. Here that's meandric system of size 4. I usually write 8 vertices. And 2 components. Here you have one component here, and another here. And something that we see on this picture is that the component can somehow interlace. So here it's in a rather simple way. It would be much more complicated how they interlace. And that explains that there is no direct combinatorial relation between the numbers of meandric systems and the number of meanders. Otherwise, the meander problem would be easy because the number of meandric systems, that's very easy. It's just a pair of 2 non-crossing matchings. Non-crossing matchings are counted by Catalan numbers. So we have size n. This is Catalan n squared, so I can write, just to be sure, explicitly formula for Catalan numbers, and we also know very well the asymptotic of that, so this will be 16 to the n times n to the minus 3 squared. So from a combinatorial perspective, it's very easy, or at least to count them. What is difficult there is to study really the components. Before stating the result, I will just give one more motivation to study the system which is not related to meanders. So what I said is that a meandric system is a pair of non-crossing matchings and here I will say again, so of size n, and here I have 2 endpoints, and the non-crossing matchings on 2 endpoints is the same than is the same as a non-crossing partition on endpoints. So that's a classical bijection in numeric combinatorics. I can maybe. So this is more just a motivation. So it's not. I will not reuse that later, but just to show you how this works. So you have. I will do an easy example because then when we double the number of points. So this is, for example, a non-crossing partition on endpoints. So here I'm not doing matchings anymore. I can have singletons, like 2 and 5 are singletons. Maybe I should move it still a bit. Okay. 2 is a singleton. I have a pair 5, 6, and I have 1, 3, 4. And non-crossing means that when I draw everything like this above the line, I don't have crossings between different parts. So I don't have 4 elements, such as the first and the third are in the same part, and the second and the fourth are also in another part. Okay, so that's the non-crossing condition. And I can transform that in a very simple way into a non-crossing pair partition by doing arches like that. So what I do is that now for every original points, I take 2 red points, and I draw an arches by following inside and outside the white blocks. Okay? So it's not a very formal definition, but it's just to say there is a very simple way to go from here to here. I divide by those to the number of points. But here I have the condition that every block are of size 2, I have only pairs, and here I can have blocks of any size. And that works, of course, only because we are using non-crossing options. So just to tell you, I can look at this as a meandric system. I can see it equivalently as a pair of non-crossing partitions on endpoints. So I will use the following notation. When I have rho pi, which is a pair of non-crossing partition, I will denote M of rho pi, the associated meandric system. Just for the following statement. And in fact, the number of components here on this side has a very natural interpretation on that side. That's why I'm introducing this documentation. And so this is in a paper of Valentin Féray and Puder, which was published in 2020. And what they prove is that, so for all rho pi in NC of n, so this is the set of non-crossing partition of endpoints, the number of connected components of M rho pi is equal to n minus the distance of rho between rho and pi. And what is this distance? So this is the distance in the hot diagram of NCN, and when I'm speaking about the diagram, it means that I have an order structure on the set of non-crossing partition, and this order structure is very standard on set partition. It's just refinements. Okay, so partition refine another if you can just split the block of the coarsest one into to obtain the blocks of the finest one, and then you just draw your order, and that defines your graph structure. You forget the orientation, that defines your distance, and magically this distance can be read in terms of connected components of the associated meandric system. It's not at all easy to see. I'm not claiming that. It's not a very complicated proof, but I find this surprising. And this is also something completely independent of meanders to a reason to look at this meandric system. Okay. So let me now state first the question and then the result. So what motivated our work is a question which was asked in this paper of Valentin Féray and Puder. And in fact, we discovered later that it was asked roughly the same question, a more precise version, as we will see in another paper which was published the same year, but completely independently. So none of this paper seems to be aware of the other one. And the question is, you take a uniform random meandric system, how does the number of connected components behave? Okay, so more precisely, what was asked, so in the paper of Valentin Féray and Puder, they were really looking at the expectation of the number of components of Mn. And what they asked is whether this behave as a constant times n. We just should write Mn is uniform random meandric system of of size. Okay. And Carvin was much more went a bit further in his experiments and okay. So what he conjectured somehow, or he didn't write precisely conjecture, but he said it should be the case, that you can find that basically the number of components is asymptotically normal. So you can find some constant kappa and sigma such that when the expectation is roughly kappa n, and when you remove the expectation and divide by sigma root n, you converge in distribution to a normal. Okay? That was the question. Both have some arguments which are not the same to show that the number of connected components or the expectation of the number of connected components is linear, so they have some linear lower bound. And what we could prove, so we were a bit in between the two questions, so we could not prove the asymptotic normality. We proved that the expectation behaves indeed as kappa times n, and also that there is some concentration, so that we have convergence in probability of the number of connected components divided by n. So that's the result. Number of connected components tends to, so there exists kappa in 0, 1, and we will see that we have no exact formula, or we have no simple formula for kappa. We will see some probabilistic interpretation and some summation, infinite summation formula for this kappa. But we show that there exists some kappa such that the number of components divided by n converge in probability to kappa. Okay? So so that's the result. If you have some question, it can be a good time. And I will use now the slide.
So you need something extra to prove GNP conjecture? You need us.
Sorry? So GNP follows, sorry, I should have said that, because this is bounded, so you can take the expectation. Yeah, the number of components is at most n, but okay, I can discuss a bit later. This we don't know how to prove.
Just the fact that it's bounded suffices to.
Yeah, the fact that it's bounded suffices to imply that the expectation. So the GNP is fine. This is still open. There is some newer result of Paul Tettner with Span-Penianson, which proves that if you look at components with a given shape, in some sense of shape, you have some central limit theorem, but not for the total number of components. So I think I need some password.
Maybe with the same capitalization as
Thank you. Okay. So first, I show you some pictures, and then I want to explain you a bit how we got this, or at least the main idea to get this result. Okay. So this is somehow a historical comment. This is to show you that the interest for meanders dates a bit. So this appeared in an article of Henri Poincaré in 1912.
Sorry, there was a question in the chat.
There is a question in the chat. Can I see it here?
Asymptotic number meanders written earlier are the constant A and C node.
No, so there is some rather precise numerics for A. I think it's something like 12 to 12.26 or something like that. And I don't think there is anything on regarding C. Thank you for the question. Okay. So that's a picture. So here you see he was looking at, he was studying some property of homeomorphism of annulus, so that's why you have an outer and an inner circle. But inside he was really looking at some kind of meanders. So he was looking at, he takes a cycle, he looks at the image of the cycle by the homomorphism, so it's another closed simple curve. And he was trying to see how the intersection point can change when you take your dash cycle, you start from the outer cycle to the inner cycle, and show the existence of some fixed points by using combinatorial argument. Okay, he didn't succeed to do this, in fact, and the fixed point theorem was proved in another way a bit later, but still, it's the first operation of meanders in the literature. So that's a uniform random meanders of size 30, so you see it's not directly easy to see that it's connected. That's why I say connected components are not so easy to see, and it can be rather complicated. That's a meandric system. So here you see, for example, that you have a small component here in the middle. If you look a bit above, you will see that in fact this middle part is constituted of 3 components, and the outer part is 1 extra component. So that's 1 with 4 connected components. And
is there a probability of the number of components that you find?
Is there a
random?
Sorry, I didn't get the question.
Random random meandric systems, and you ask how many components?
Yeah, so that's what we will be looking at, and in fact it grows linearly with n. That's our result. But the number of components will grow linearly with n. So that's a bigger meandric system. So I didn't. This is taken from an article. An archive from Borgad, Weil, and Part that I will mention also a bit later. So here we have 1 million points. Only the largest 300 components have been drawn to make the picture easier, and the color, they are colored by connected components. So the largest one is colored in red, the second one in yellow, third one so on, and then between 6 and 300 largest connected components, they use blue to purple with shading. Okay, and you see that also intrication of the largest connected components first, they are really complicated, and they are also imbricated in complicated way. And so this is a somehow combinatorial picture. You have your 2 non-crossing matching above and below the line, and this is more the random maps, random lattice picture decorated with some loop model. Okay, so here you have your 4-valent map, and it's drawn with a canonical embedding in the unit disk, which is here the Qt embedding, and you see again the largest loop which are drawn on the sphere, on the disk. Sorry. And that was just related to this interpretation of number of connected components of the system. This is a diagram of the non-crossing partition lattice on 4 elements. So you see here the non-crossing partition. It's common to draw them on a circle rather than on a line as I did on the blackboard, and that's the order by refinement. And I didn't say it's here, but of course the consequence of our result is that if you take 2 non-crossing partition uniform of size n uniformly at random, so I use this U to say uniformly at random, then the distance in this diagram between rho and phi divided by n will converge to 1 minus kappa. So of course if you take this is integrated. So you have concentration of the 2-point distance in this lattice of non-crossing partition for large n. So in this sense, it's a bit what happens like in a large dimension hypercube, where you have also concentration of this 2-point distance. Okay. So now back to a bit more math, and I will try to use it to explain to you the proof strategy of the main research. It's not that complicated, in fact, with a good point of view. So we start with some very simple lemma, and almost an observation. It's the following thing. If you take any meandric system, so for example, for the moment, I'm not speaking about a random one, but you take a meandric system, and you have a probabilistic interpretation of the number of connected components, and more precisely, the number of connected components divided by n. I claim that it's 2 times the expectation of 1 over the size of the component containing a random point. Okay? So here, n is not random, I said it. So what is random and what refers this expectation to is this in. I choose one point in my meandric system uniformly at random, and I look at the components containing this point. Okay? And I look at the size of this component. Okay? I take the inverse size and I take the expectation of this inverse size. And I claim that this is up to some factor the number of components. And this is very, very easy. Because you have just take a uniform point in your meandric system or a uniform integer between 1 and 2, and the expectation is just 1 over 2n times the sum. Okay? And in this sum, each connected component will contribute 1, because you sum 1 over the component size. Okay? So each connected component contributes 1, so you have the number of components. And that's it. So that's why I'm saying it's an observation. So as I told you before, I'm interested of the number of components of a uniform random meandric system. Okay? And here, at least until the last slide on this proof strategy, I will look at the expectation. So I will show you the weaker GMP form of the theorem, that the expectation divided by n converges to a constant. So when I look at this expectation, this is divided by n. This is twice the expectation of the inverse component side. But here, unlike here, the difference is that now both the meandric system and in are taken at random. Okay, so if you want, I take a uniform random marked meandric system, a meandric system with one specific point which is marked, and I look at the component size, the inverse component size of this marked point. Okay? So this is very easy, but why is it interesting? That's more the question. So why is it interesting? It's because when you look at the left-hand side here, this is should do something like that. This is something global. The number of components, you need to see the whole meandric system to count it, and it can be a bit. You have some very large components which go from one side to the other, as we have seen in the simulation, so it can be a bit nasty. Here, if you're lucky, I say most of the time, when you look at your in, you can look at a small neighborhood of in, and you will see the component of in, so you know the size and you know this quantity. So this is, or at least this can be, a local quantity. And because it's a local quantity, to study it, we will look at Mn locally around this random point I sub n. And in fact, we will be able to prove the convergence by proving some kind of local convergence of the meandric system around the random point I sub n. So that's really one of the main ideas in the proof. So the question is now, to study this will be, what does Mn look like in the neighborhood of a random point, and in what is the local limit of this Mn with a marked point? And in graph theory, people call that Benjamin-Mishram convergence of graph, when you take like this a vertex at random and you try to find some limit of the graph locally around that vertex. Okay, so what does it look like? Yes?
What is the meaning of local? Local on the first curve or on the second curve?
It's local, it will be really local on the first curve. So here it will be local like this. But in fact, sorry.
It means that the components are very localized.
Yeah, exactly. And what we will see is that, in fact, if you will look at local around the red curves, it will be the same. Because typically it's rather, the red components are rather localized. That's somehow a corollary of what we're doing. And I can discuss that a bit later. So sorry. So it's not very hard, in fact, at least with the hands, to say what should the meandric system look like locally. Just with the following observation. So a non-crossing partition. So remember, it's a non-crossing partition above and one below the line, and they are independent. So let me look first above the line. So your non-crossing partition, it's rather classical to encode it as a dig path, okay? By saying when I have the left leg of an arch, I put an up step, and the red leg will be a down step. Okay, so here I cannot really see, but it's 1, 2, 3, 4 up steps because I have 4 leg steps, 3 down steps, and so on. Okay, so when I take a point. Okay, so if I take a pair of them, I have a pair of dig paths, and I will usually represent them like this by just reflecting the one below. So now when you take your random point IN and you want to look locally what your meandric system look like, so I fix the radius R, that's what I will do later, and I look at my meandric system on the interval IN minus R, IN plus R. I should look at the path of this interval. So there is a very nice thing in this bijection between fixed and between non-crossing matchings and path is that it's purely local. So okay, if I know the path here, I have some up step here, and I have the down step which is here. So by corresponding, I mean that they are at the same height, and everything in between is above. And this corresponds to an arch here in my meandric system. And to know that, I just need to look locally on the path and locally on the meandric. And locally, when you look locally in a dig path, it's known and not very difficult to see that you have an unconditioned random walk. Okay, so a uniform random dig path will be a random walk. Simple random walks which is conditioned to stay above the line and to finish at time 2n at height 0. But when you look around the random points, you're rather far from this conditioning at this end that it should end at height 0. And you're also rather high, you're typically at height square root of n. So the fact that you're conditioned to stay above the line, you can forget about it. So typically, this looks like an unconditioned random walk, and this also. Which tells you a bit what should be the limiting object. So the limiting object, I could have written that in terms of random walks, but I prefer here because it's simpler to draw to use this arrows. So right arrow will correspond to what I had up steps before, and left arrow will be down steps. And I want to match up steps to down steps, so I want to match some right arrow with some left arrow, okay, to do some arch. So I take two infinite sequences of these independent uniform random symbols, okay, one above the line, one below the line. They correspond to my two non-conditioned random walks. And then I will construct arch. There is a unique non-crossing way to construct some arches, so that I have always a right arrow match with a left arrow. Okay? And this really corresponds to what I was doing before in my random walk, to match an up step to some down step, which is at the same height, and everything in between is above. And so that's define what people are calling, so either the uniform infinite meandric system, UIMS, or some other name which is a bit less precise, but a bit more fun, which is the infinite noodle. And so this was introduced in this paper of Curien, Cosmas, Sidaro, Vicius, and Tournier, and this is exactly what turns out to be the local limits of this marked meandric system. Okay, so you just take this row independently, uniformly at random, and you match things in a non-crossing way above and below the line independently.
Does the statement use probability 1 or what?
Yeah, so it might happen, that something is not matched, because for example, if you have only right row above the line, things will not be matched. It's still true, I think, that there is a unique non-crossing way. Okay, maybe not. Okay, so let's say with probability 1 there exists a unique non-crossing way to match. And something which will be important later is that everything will be matched. So, of course, here I'm looking at a restriction, so this is not matched to anything on my picture, but it will be matched eventually to something later. Okay? Okay, so we proved indeed that when you look at your uniform random marked meandric system, it converges to this infinite noodle, I will call it like that, marked in 0, so it's translation invariant, so you can mark it wherever you want, it doesn't change anything, so I will always use this infinite object, I will always mark it in 0. In the local sense, so what does it mean? That means that for each radius, the restriction of your uniform meandric system to a window of radius r around in will converge to the restriction of m infinity to a window of radius r around 0. Okay, minus r. And just to tell you what the proof is, maybe I will just keep that. It's basically using, you have to play a bit here. There is a trick that's with the marks, but it's not very important for what I want to say. And now, okay, this is nice, but what we are interested in is this quantity, the inverse component size of in in my random meandric system Mn. So I need some kind of continuity argument. And what we prove is that indeed, if you look at this functional, so it's a functional on the set of meandric system with marked elements, and the functional associated to an object like that, the inverse component size of the marked elements. This is continuous, so you have to be a bit careful. It's not continuous on the full domain. It's continuous on the subset of complete marked meandric systems. So what means complete? I never state that for the moment. So the thing is, because here we take restriction when we define our topology. So you see, when you do restrictions, that's what I was saying, you have things which are not connected to some other point in the window where I do the restriction. So I have to extend a bit my space to define the local topology and to include objects which have some open arc. And if I have some open arc, I could have some problem, and I will not have this continuity. So this function is continuous on the set of meandric systems which don't have open arcs, and that's what I was saying just a bit before, is that the infinite noodle does not have open arcs. So for us, that's fine. We will be able to conclude. So now when you have this, you know that your Mn marked with in converges to the infinite noodle. This is continuous on the set of complete marked meandric system. The infinite noodle is almost surely complete, and then you use what is called the mapping theorem, and you can apply this functional to your convergence, and you have that 1 over the component size of Mn converge in distribution to the inverse size of the 0 in the infinite meandric system. Just a comment, this could be infinite, so the inverse could be 0, but still it converges in distribution. And because they converge in distribution and it's bounded by 1, you can take the expectation and you have your result. Okay, you have your result because I recall you that this was 1 over n times the expected number of connected components, and this you just define this as a constant kappa. Okay, so I told you this has some probabilistic interpretation, so this is a probabilistic interpretation. and okay. So I told you, in fact, we have a bit more than the convergence.
Sorry.
Should I So yeah. So this is mainly the proof ID. So I told you we have more than the convergence of the expectation. In fact, we have convergence in probability. And to get that, you need to have some stronger version. I will just tell you in word what this is. We need to have some stronger version of this local convergence, something which is sometimes referred as quenched Benjamin-Ishram convergence. So what this means, it's phrased in terms of random measure. So what this means, in fact, is that you want to have some convergence conditionally on the meandric system. So for any meandric system, you define a measure on the set of random on the set of marked meandric system, which is what you have by taking the root at random in this meandric system. So you sum over I to the 2 ends the Dirac in the marked meandric system marked in I. So for each meandric system, you have a measure. That's a bit what you do when you do random matrix and you look at the eigenvalues. And then this measure converge in distribution or in probability, that's the same here, to some deterministic measure, which is the law of the meandric, the infinite noodle. And when you have that, you can use a version of the mapping theorem for random measure, and you can conclude that you have convergence in probability here. It's a bit more technical, but the idea is roughly the same. It's a bit more difficult to prove the quenched Benjamin-Ishram convergence of the meandric system to the infinite noodles. The one that I showed you is the annealed Benjamin-Ishram convergence, but the ideas are roughly the same. Okay, so I don't know. I will maybe skip this part. So we have some formula for kappa as a large sum over meanders with some big sum of products of Catalan numbers. There are some funny things which appear here. I would just like to finish more with some open questions. So the first one is was in this paper of Curie, Cosma, Sidarovicius, and Tournier. So that's the ones that I mentioned where they introduced the limiting object. They were not interested in finite size meandric systems. They were directly looking at this infinite noodle, and they were looking at it from a percolation point of view. Okay, because you have you have your line and you have your arches, which are random edges if you want. And the question from percolation point of view is, can you find an infinite cluster there? So what is obvious is that this number of infinite clusters is almost surely a constants because it's in that translation invariant in an algorithmic system. And what they could prove is that in fact this constant should be 0 or 1. So meaning that either it's almost surely 0, either it's almost surely 1. It cannot be like 0 with probability 1/2 and 1 with probability 1/2 because of the algorithmic argument. So that's one of these two things hold, but they could not decide which. They conjecture that in fact there is no infinite cluster. So it's almost surely 0, but it's still an open question. Related question when you look at that, and it's also related to the formula we have to compute kappa, is if you look at the size of the component of 0 in the meandric system, how fast does it decay? And it seems that it has some polynomial tail. So I have a colleague which has done some computer experiments, and it seems to be like k to the minus 1/4 roughly. So it's a rather slow decay. And this seems to confirm that there is no infinite cluster also. And in fact, there is now a precise conjecture for what should be this exponent, and it's a quadratic exponent, a bit like in the Leander problem, but more simple here. So in fact, this exponent, okay, a simple quadratic expression. And in this paper also, which was last December on arXiv, they have some partial results on this exponent. And so that's really looking at this infinite object. But this kind of problem, you have really a kind of dual point of view, which is on the finite object, and it's by looking at the largest components. So here we have some result on the number of components, as it's typically linear, but as Sanjay was mentioning, what this means, in fact, is that most of the components are really localized, really rather small and simple. And it does not, our technique is not well suited to study the largest components. And here there seems to be also some rather interesting things going on. And Karlin, in his paper, in addition to conjecturing the asymptotic normality of the number of components, he was looking at the size of the largest component. And here the size of the largest component seems to be polynomial, but sublinear, and of order n to the 0.8. And again, in this paper of Borgard, Wine, and Park, they said that this alpha should be some rational number, and again, some quadratic number, sorry. And again, this conjecture comes from quantum field theory. And in fact, it's not 4/5, but it's this, and it's close to 0.79, so it's numerically it's rather close to 4/5. And it's not, they conjecture also that it's not only true for the first loop, but also the second loop, the third loop, and in general the jth largest loop if j is fixed. And they have also some polynomial lower bound for this largest component. So there are still many interesting, but I think rather difficult problems in this area. And I have a slide, but I won't go over it, just to say there is really a relation between the last two slides. So I recall you beta was this exponent for the decay of the component size in the infinite model. Alpha was the exponent for the largest component size in the finite model. And there is no, it's not formal, but with some first moment arguments, there is some heuristic for why these two exponents are related by this simple relation. And it's also what appears in the link between in one case there is a partial result. In both cases they have some partial result, and that's because of this connection. The two problems are really related. That's my point.
So it's minus n to the minus alpha beta in the last line.
Here?
No. In that line, but for n alpha beta, isn't it n minus alpha beta?
It's n minus alpha beta, right. Yeah, it's minus come from here. Sorry, all the time. Thank you very much.
Any questions?
The last questions you asked, they seem to indicate that in fact this infinite noodle is just critical.
Yeah.
Is there any natural way to
on this one you mean okay. They are related.
You give exponents, there is no infinite. You expect there is no infinite component, but there are large components decaying somewhere.
Yeah,
this looks very much.
Yeah, I agree.
So, is there any one parameter family of models, so that you would see that this one is exactly the critical point, and then you have a phase in which a dense phase and.
No, I don't have that. I have thought a bit of that, and it's not clear. So you could try to bias your random walk if you create that for random walk, but that makes really a lot of not protected points, so it's not really what you want. And you don't have you have only things which are subcritical with very small components. You don't have the supercritical regime. In the paper of Kamgin, he's looking at so in the finite model you can look at you can put weights, and he's putting. So how does it work? I don't know exactly how it works directly on the arch system, but you have some encoding by trees, and he's looking at simply generated trees. And but it's not clear. He has always critical the same kind of exponent n to the 4th 5, so it does not. First, it's not clear how to do something like that at infinity. Or you can put weights depending on the length of the arches, but you don't really know how to study that correctly. And in the finite model, it does not change the critical exponent for the largest component, so it seems to stay in criticality somehow. So it was a long no.
Maybe naive question related to that, but the components are they related to the blocks of the non-crossing partitions?
No, no, because you really when you transform your arch system in the non-crossing partition, you're really using just one arch system. Which is very complicated when you look at components in meandric system is that you have your two arch system and it can really you can have long arch going in one direction and then in another.
The arcs aren't they following the boundaries of connected union of the blocks. I mean.
Yeah, but so you take two non-crossing partitions. Yeah, maybe there is a description.
Because here you could think about the
position
infinite.
Description as like the smallest block.
You have maybe you have natural generalization of law on non-crossing partitions, not just a uniform one, but.
Yeah, but I think that was the idea of looking at this simply generated. So I think he speaks about simply generated meandric system. So because it's a tree structure, you can have some generalization by putting weight depending on the degrees of your vertices of the tree. But this seems to stay somehow critical. And it's not clear. I try to think if we can do that directly on the infinite noodle, but it's not clear. But clearly, yes, it's a critical. It's a critical system.
Questions?
That generalization of the first conjecture with several components. The first conjecture you mentioned.
The enumeration conjecture on meanders. I don't know. That's a good question.
Questions? Let's thank Valentin Féray.